All right, today we are looking at Unit 7, Equilibrium, Topics 5 and 6, Magnitude and Properties of the Equilibrium Constant. So we are going to explain the relationship between concentration and very large and small equilibrium constants. We will also see how changes to a reaction affect the equilibrium constant. All right, first we will look at the magnitude of the equilibrium constant, which is represented by a capital letter K. So when at equilibrium, if the concentration of the product is more than the concentration of the reactant, then K is going to be greater than 1. So we're going to take a look at how this is true with the equilibrium constant formula. So to look at the equilibrium constant formula, again, we have the concentration of the products over the concentration of the reactants. We would list each product and reactant and raise them to their power of their coefficient. So if we have if this fraction is greater than 1, then that means that we have to have a larger number on the top and a smaller number on the bottom in order for that fraction to be greater than 1. So that means that it favors the products in this reaction. We're creating more product than reactant. Now, if the concentration of the reactant is more than the concentration of the product, then K is less than 1. So looking at our expression, that means our fraction will be less than 1. And in that case, it means that we have a smaller number of products in the numerator and a larger number of reactants in the denominator, therefore getting a value less than 1, a fraction. So in this case, we're favoring that reactants side of our reaction. And lastly, if the concentration of the reactant is the same as the concentration of our products, that ratio is the same, then K is equal to 1. So that fraction will be 1, meaning we have the same number in the numerator and denominator to get that. That is a lot more rare. We don't see that often at all. So thinking about what happens to our number, we don't have to be able to memorize if K is greater than 1 or less than 1 and what that favors. We can think of it in terms of this fraction and what happens to the fraction that makes the number smaller or larger. And then does it favor having a larger number in the numerator, the products, or in the denominator and the reactants? So thinking through it logically, we don't have to memorize things necessarily. So let's take another look at the values of K. So we're given a reaction, its equilibrium constant, and whether it's greater or smaller than 1. And we want to know what species or what chemical will you find the most of or be in the highest concentration at equilibrium. So looking at this first one, we've got a reaction of hydrogen and oxygen making water. We can see our equilibrium constant is 1.7 times 10 to the 27th power. That value is greater than 1. So that means to be greater than 1, you would have to have a larger numerator. Since our numerator is the products, we have to have the products being in a larger quantity. So our highest concentration in equilibrium would be our products, or water in this case. For the second reaction, we've got NO and Br2 making NOBr, and our equilibrium constant is 1.32 times 10 to the negative 32. That's a very small number. So it's much less than 1, which means to have a very small number, a number less than 1, we would have to have a larger denominator. Our denominator is our reactants every time, so that means we would have to have more reactants, NO and Br in this case. Those would be in the higher concentration at equilibrium. So we can use our equilibrium value to help us decide if we're going to have more products or more reactants at equilibrium. Let's try another example. So which of the following reactions will produce the least amount of products at equilibrium? So if we're trying to make the least amount of products, that means we want to favor the reactants over the products. We want more reactant than product. So looking at our 3 reactions, we're not going to find it in how the reaction's written, but we're going to find it in the K value, the equilibrium constant. So if we want to have the least amount of products, we want to favor reactants, we need a larger denominator. We want to have that fraction be much smaller. So we want the smallest value possible to favor the reactants. And so that would be reaction C with the smallest equilibrium constant. Our second question, which of the following reactions will produce the most amount of products at equilibrium? To have more products, that's going to be a greater numerator in that fraction. So that's going to give us something greater than 1. So that would be reaction A. We have a much larger value, so we're going to favor our products. Now it says at equilibrium, which reaction would be closest to 50% products and 50% reactants? If we've got a 50-50 mix, then that's going to be a K value of about 1. So that would be letter B because it's 0.8, and that would be closest to 1.0 out of the 3. So that's another way we can use these, is to determine which reaction favors reactants or products, or is at equilibrium that's close to 1. The last thing to look at with the magnitude or size of our equilibrium constant is when our equilibrium constant is much, much greater than 1. Then the amount of product is so much that the reaction basically goes to completion. So let's talk about what that means. So if our K value has a really large value, a lot of these are in scientific notation, so that would be a really high positive exponent in our scientific notation. That means that we create so much product and barely any reactant that we say the reaction basically forms only product. It's such a tiny, tiny number of amount of reactant that it basically is negligible or doesn't matter. Now the opposite can also be true. When our K value is a lot smaller than 1, and again, our values are often given in scientific notation. So this would be a large negative exponent to get a very tiny number. Then the amount of product is so small that the reaction barely proceeds. So we basically get no product. So that's what we can think about when the K value is really big or really tiny, those extremes. Okay, now we're going to take a look at properties of our equilibrium constant and 3 ways we can manipulate a reaction and how that corresponds to its equilibrium constant. So first, we're going to talk about reversing a reaction. So if a reaction is reversed, K is inverted. So what does that look like? Well, we've got our starting reaction here. So this is what we're going to keep referring back to see what the change is that's made. So for our first change for the reaction, this one is reversed. We can see that the product, letter C, is now the reactant, and A and B are now the products. So that has been reversed. What we want to know is what is our new value of K? Now let's take a look at the equilibrium expression to help us. So the original one had the product C on the top and A and B on the bottom. Now ours has A and B on the top and C on the bottom. So if the expression is flipped, that means our K value must also be flipped. Well, we can't just flip it over and write it upside down. What we do is we take the inverse of it. So 1 divided by 2.12, again from our starting reaction, times 10 to the negative 4th. So we can't leave it as that fraction. We want to go ahead and solve it. So if we do that and do 1 divided by 2.12 times 10 to the negative 4th, we get still a pretty large number, or not still a large number, now we have a large number, 4.72 times 10 to the 3rd. So that's about 4,720 versus our 0.000212. So that's what we do with K. If we reverse it, then we flip and do the inverse of our value. So we don't have to have things to plug in for A, B, and C. As long as we have our equilibrium constant, we can manipulate the reaction and change the constant that way. The second thing we can do up above, it says when the coefficients are multiplied by a value, k is raised to the power of that same value. Well, let's see why that is. So our starting reaction, again, has A on the left, C on the right, so that's consistent, but our coefficients have changed. We can see A goes from having a coefficient of 2 to now it's just 1, so it's half of what it originally was. And B and C both used to have a coefficient of 1, and now they're each 1/2. So let's see how that affects our expression. Down below, we still have our product C on the top, A and B are reactants on the bottom. However, their exponents have changed. A has gone from being an exponent of 2 or squared to having an exponent of 1. C and B have gone from having an exponent of 1 to 1/2. So when that happens, everything is being raised to that smaller power, to that 1/2 power. So how do we find K? We're going to take our K value, our original one, 2.12, times 10 to the -4th, and we are going to raise it to that 1/2 power. Now, if you don't know how to put a 1/2 in, or you want to write it as 0.5, that's fine. In our calculator, we're going to do let's see. I put it in parentheses personally, 2.12 times 10 to the -4th. And then I'm going to close my parentheses and raise it with the little caret key. And I'm just going to put in 0.5 for half. And I get 1.46 times 10 to the -2 as my new equilibrium constant. So this is a really good one to try out on your calculator and make sure you're getting consistent answers. So when we reduce the coefficients, we can see that our K value is actually larger in this case. All right, last one. So this is when we multiplied everything by 1/2, all the coefficients. So we raise K to the 1/2 power. All right, our last one, we can see a couple things happening. I can see that my C's are on the left now, so it's been reversed. And I can see my coefficients are larger. All the coefficients have been multiplied by 2. So let's look at our expression and see what changes. Again, from this starting one to now. So here we can see that actually this one is written incorrectly. Let's fix this one. If it's incorrect on your paper, make sure you're fixing it. So it should actually be our products. So A to the 4th and B to the 2nd on the top, because those are our products, and then C squared on the bottom. So we can see that comparing to our starting one, our C is on the bottom now and is squared, and A and B are on the top, and they have both increased their power. So I'm going to go ahead and let's think about what we need to do to K. So I'm going to have to do that up here because I ran out of room. So our K value, original K value is 2.12 times 10 to the -4th. That value is going to now be raised to a higher power. So all of the coefficients have been multiplied by 2. So I'm going to raise that to the 2nd power. And it has been reversed. So I'm going to put all of that under 1 and recalculate my K value. And that's what I'm going to put down here. So I'm going to put 1 divided by, I'm going to put this in parentheses, 2.12 times 10 to the -9th. And I'm going to, or excuse me, -4th, my bad. And I'm going to go ahead and square that and hit enter. So I got 2.22 times 10 to the 7th power. All right, so when we invert it, changes flips the reaction, and when we multiply the reaction by a coefficient, we raise the K value to that number, that coefficient number. So those are 2 of the 3 ways we can manipulate a reaction and how the K value responds to that manipulation. Let's look at one last one. So the last way we can change a reaction or manipulate it is when reactions are added together, the K value for the overall reaction is the product of the K's for the reactions that were added. So what does that mean? It says calculate the value of Kp for the reaction at 25 degrees Celsius. And we are given a reaction, so we got NOBr making NO and Br2. And we have a couple of reactions given to us. So just like in the last unit, we want to start with just one chemical and find it and see what we need to change about it. So I need my NOBr. I can see it in my second reaction here. It's on the right side of the arrows where I need it to be on the left side of the arrows up here. So I'm going to need to flip this reaction and then take care of K and see what happens there. So I've got 2 NOBr, and I'm going to flip it around and put the reactants on the product side, N2 gas plus Br2 gas plus O2 gas. So that flips my reaction. Well, what does that do to my K value? Well, it's now going to be 1 over my original K value, and I'm going to recalculate that. So I'm going to take 1 and divide it by 2 times 10 to the negative 27th. That's my K value. And we get a new K of 5 times 10 to the 26th. All right, 5 times 10 to the 26th. That gives me my NOBr. It also gives me my Br2 on the right side, which means my other chemicals are going to need to cancel. So my second reaction has the NO, my first reaction has the NO. It is not on the correct side either. So I'm going to also need to flip this reaction and do 1 over my equilibrium constant. So if I flip it, I've got N2 gas plus O2 gas, making 2 NO gas. And we can see that we have that NO piece. And then everything else should cancel out. So N2 is on opposite sides, so is O2, so those cancel. Well, my K value for my first reaction, I had to flip it, so I'm going to do 1 divided by that value. So 1 divided by 1 times 10 to the 30th. And I get 1 times 10 to the negative 30th because I flipped it and inversed those that value. So now that our K values are set up to find the overall K value for this reaction, I have to do the product of the K's for the reaction. So K for my overall is going to be equal to, I'm going to call it K2 and K1 because it was the second and first reactions. So I'm going to do K2 times K1 to get my overall equilibrium constant. So 5 times 10 to the 26th multiplied by 1 times 10 to the negative 30, and we get 5 times 10 to the negative 4th as the equilibrium constant. Remember, there are no units on our constants here. So that's the third thing we can do. In this particular case, we had to flip both reactions, and so we just had to do the inverse, but we could also multiply them by coefficients. The key here, I think the biggest key, is to make sure you're doing this part, recalculating from here down to these, okay, so that those are accurate before you do your last step down here, where you've got the multiple K values that you're multiplying with each other. All right, whatever questions you have, see me in class, and have a great day.